Welcome to this video where we will talk about how to use Shearwall Pro. Shearwall Pro has 6 main sections for input, and all are required to be completed to generate the output. These areas are project data, design criteria, building data, roof gable data, diaphragm data, and shear walls. For multi-story buildings, some of these sections expand, and input for each diaphragm and shear wall level requires more input. It might seem like there's a lot of information to grasp here. However, after using Shearwall Pro a couple of times, everyone who has used it agrees that everything is intuitive and makes sense. All right, let's get right into it. The project data is the simplest section to fill out. Enter the name of the project, the client name, and the site location. For this example, we're going to stick with our trusty 30 by 40 shop that we have been talking about in previous videos. So the project title is 30 by 40 shop. The client is the awesome client, and the site location is in Clackamas, Oregon. All right, we've got our project data filled out. All right, let's move on to design criteria. There are 10 inputs in this section, and most are almost always going to be the same. However, there are 3 input values that need to be checked and verified for every project, as they can be different each time you use Shearwall Pro. Location. The correct zip code for the building is required to be entered. The seismic loads are tied to the zip code and can sometimes change a lot over short distances. Next is wind exposure. Most buildings in urban and suburban areas are going to be exposure B. Sometimes, when a building is in a more open area, exposure C is required. Basic wind speed. Every building jurisdiction publishes a basic wind speed for which all buildings in their jurisdiction shall be designed to. Some jurisdictions have multiple basic wind speed areas. To find the basic wind speed for your project, you can almost always find it by typing basic wind speed my jurisdiction into Google. For example, basic wind speed City of Portland or basic wind speed Thurston County, Washington are some examples. And make sure you enter the ultimate wind speed. That is important. Floor dead load. It is important to get an accurate floor dead load because the floor dead load is used to resist the uplift at the shear walls that support the floor system. A table of typical floor system weight is shown below here. Floor live load. For most residential uses, the floor live load is 40 pounds per square foot. Roof dead load. It is important to enter an accurate roof dead load because the roof dead load is used to resist the uplift at the shear walls that support the roof system. A table of roof system weights is shown below. Roof snow load. This information is typically provided on the same web page as the basic wind speed for your jurisdiction. This doesn't often have an influence on the calculations. However, on occasion in high snow load areas, it does. In high snow load areas, some of the snow load is included in the seismic calculations. Seismic calculations are a function of the weight of the building. The more mass the building has, the higher the seismic loads. In heavy snow areas, including some of the snow load in the seismic calculations is sometimes required, where large amounts of snow are on the roof for an extended period of time throughout the year. Wall dead load. A wood-framed wall with plywood and siding on the outside and sheetrock on the inside typically weighs about 8 pounds per square foot. This wall weight is used to help resist the overturning forces that the hold downs resist. This is an important number to have correct. Assumed soil bearing capacity. For nearly every project, the assumed soil bearing capacity is 1,500 pounds per square foot. If a geotechnical engineer or a soils engineer, as they are sometimes called, is hired for your project, they can sometimes provide a higher bearing capacity if the soil will support it. On rare occasion, the building department might indicate a lower allowable bearing capacity. Site class definition. Nearly every project in the Pacific Northwest will be in Site Class D. If you aren't sure what to put here, use Site Class D unless you are positive another site class is appropriate for your project. All right, let's move on down to building data. There are four main areas in this section: grid lines, diaphragm names, roof info, and diaphragm info. All right, let's get into it. Grid lines. Shearwall Pro calculates all of the loads to the shear walls based on the grid lines they are on. All shear walls must be on a grid line. If you have a multi-story building where shear walls exist at one level and not at another, the grid line needs to be defined so it can be used at the level it exists at. Every building has a primary direction of load: longitudinal and transverse. The longitudinal direction is typically the direction of the main roof ridge, or the longest dimension of the main body of the building. The transverse direction is then 90 degrees perpendicular to that. Every grid line needs to be assigned a distance from the datum and a load direction. Every direction will have one of the grid lines be a datum, and the distance from the datum for that grid line is 0 feet. All other grid lines are measured from there. In this example, grid line A is the datum and grid line 1 is the datum. So we can see here that the distance from the datum for grid line A is 0 and the distance from the datum for grid line 1 is 0. Diaphragm names. Every diaphragm is given a name. The upper diaphragm is predefined as roof because the roof is always the highest diaphragm in a building. Shearwall Pro allows you to define 3 more diaphragm names. They are typically names like upper, main, and lower, or second and first, or whatever you decide. Just be consistent with your naming convention between the calculations and your drawings. Diaphragm heights are defined as the distance from the foundation to the diaphragm. This is a total height for the building. The diaphragm height, in this example, the diaphragm height is 12 feet. For a two-story building example, the diaphragm height might be something like 20 feet and have an upper floor diaphragm of 11 feet. Assuming the upper floor system is about 1 foot in height, this would indicate a main floor wall height of 10 feet and an upper floor wall height of 9 feet. If you add 10 feet plus 1 foot plus 9 feet, you get 20 feet total to the roof diaphragm. This is an example of maybe a slab on grade or a post and beam floor system, and this is an example of where floor joists sit at the main floor. In both cases, 20 feet is assumed to be the height to the roof. You can ignore small measurements like this 1/4 of an inch right here. That's fine to ignore that. Roof info. Shearwall Pro calculates the mean roof height, which is important to the wind load calculations. Shearwall Pro uses the ridge height value to make this calculation. In your building, select the highest roof ridge above the wall plate and enter the value here. Diaphragm info. Enter the longitudinal and transverse dimensions of the body of the roof diaphragm. Also enter the pitch of the roof of the main body of the roof. So again, longitudinal and transverse. The longitudinal dimension is 40 feet and the transverse dimension is 30 feet. Roof gable data. For each of the two primary directions, longitudinal and transverse, there are three boxes where you must select which type of surface exists: roof surface, wall surface, or no surface. Shearwall Pro divides the roof into three main areas, and the type of surface is assigned to each. Wind loads are higher on a vertical surface than they are on a sloping roof surface. So if you are ever in doubt, selecting wall surface will always produce higher loads and ensure the building is designed to withstand any code prescribed loads. Now, in this building, I have put a dormer in here just to illustrate how you assign what happens at the dormers. Looking at the roof, in the longitudinal axis, there are three main areas that need to be assigned a surface type. The main area is always the middle, and that surface exists on every building, so you can only select roof surface or wall surface. In this building, because the roof gable has end walls and the middle area is a triangle, it is assigned wall surface. The left of middle and right of middle areas are almost always triangles. Looking at the left of middle triangle, there is nothing because the roof slopes down towards the rear wall. So for left of middle in the longitudinal axis, we assign no surface. The building has a dormer that overlooks the front wall, grid B. So wall surface is selected for the right of middle triangle. Next, looking at the transverse axis of the roof, we project an imaginary line from the top of the wall on both sides of the building that project up towards the ridge. The slope of the roof is the pitch of the roof assigned in the diaphragm info above. This creates our three surface areas. Notice that the middle area for this building has a trapezoidal shape and has some wall area in it from the dormer near grid 1. Also, the left of middle area has some roof in it. In this case, we select wall surface for the left of middle area because there is some vertical wall surface. Shearwall Pro assumes the entire surface that is left of middle will be wall surface. Next, select roof surface for the middle area because it is primarily roof, and then select roof surface for the right of middle, and Shearwall Pro will calculate both of those areas as roof surface. Diaphragm data. There are three main inputs for each direction that require inputs for each diaphragm defined in the building data section above. Diaphragm dimensions. Enter the longitudinal and transverse dimensions for each diaphragm. The diaphragm dimensions are copied from the diaphragm info above, and as more diaphragms are added, the input boxes for each diaphragm show up and you can change the diaphragm dimensions here. On occasion, the diaphragms change sizes throughout the height of the building, and Shearwall Pro allows you to account for that here. Number of walls. This is a total number of walls in each direction that are perpendicular to the direction you are considering. By default, each building starts out with 2 walls, the 2 exterior walls. If the building has interior walls, they must be accounted for here. The walls are part of the building's mass and are accounted for in the seismic loads. Wall weights. The wall weight value is taken from above. However, on occasion, the walls at one story might weigh significantly more or less than the walls of another story. If that is the case, Shearwall Pro allows you to account for that by changing the wall weights at each level here. Okay, now let's move on to the good stuff. Shear walls. Before you start defining the shear walls, some information at the top of the shear wall table for each diaphragm needs to be completed. 1. Wall weight. This information is copied from the diaphragm data above. Verify it is correct for the diaphragm you are designing shear walls for. Roof weight. This is the dead load of the roof and is copied from above. On occasion, diaphragms can have very different weights from one story to the next, and Shearwall Pro allows you to account for this here. Wall height. This is different than diaphragm height. Enter the heights of the walls at the story you are working on here. Straps or hold downs. Use this pull down menu to select straps or hold downs for the entire diaphragm. Each hold down can be individually changed later if needed. Hold downs are used at the foundation level and straps are used for story to story connections. Shear wall table. Notice the input table already has all of the grid lines that are defined above and the distances from the datum and the load direction. To enter data in the shear wall table, it's easiest to orient yourself or your perspective such that the zero datum line is at the left. Using this convention, in this example, grid A is at the left side of the building and everything measures from there. At grid A, for grid line to the left, select None from the pull-down menu. And under grid line to the right, select B from the pull-down menu because that is the next grid line receiving lateral loads. At grid line B, select A for the grid line to the left and select None for grid line to the right because there are no grid lines to the right of grid line B. For the transverse direction, orient your perspective envisioning grid line 1 at the left and grid line 2 at your right. And everything works as the same from before. For grid line 1, enter None for grid line to the left and enter 2 for grid line to the right from the pull-down menus. Finally, for grid line 2, select grid 1 for grid to the left and select None for grid line to the right. For a one-story building, at the top story of every building, the aligns with grid above column can be ignored. This is an advanced topic that will be covered in another Shearwall Pro lesson. If you entered the wall height at the top of the table above, then there should be wall heights automatically entered at every grid line you have defined. Shearwall Pro automatically uses the value entered at the top of the table. However, occasionally some walls at a given diaphragm level are a different height than the rest of the walls at that level, and this allows you to change the height of the walls individually at each grid line. For most projects, you will use the standard height defined at the top of the table. For some length of shear walls, enter the sum of the lengths of all shear wall segments you have designated as shear walls at each grid line. If you have designated one wall segment at the shear wall for a particular grid line, enter that. If you have designated multiple wall segments as shear walls on a particular grid line, enter the sum of the walls that you have designated as shear walls. Shearwall Pro also needs to know the length of the shortest shear wall on every grid line. If you have designated one shear wall at a grid line, enter that. If you have designated multiple wall segments along a grid line, enter the length of the shortest shear wall. This is used to calculate the uplift forces and assign hold downs and straps. Tributary width is defined as the width that which a structural member supports. In this case, the tributary width is half of the length of the span of the roof trusses or floor joists above. In this case, because the building is 30 feet wide, the tributary width is 15 feet. Enter that for grids A and B, because they are the load-bearing walls that support the roof trusses. Because grids 1 and 2 do not support any vertical loads, enter 0 for those grid lines. On occasion, you might want to have a hold down at one end of a shear wall and a strap at the other end. The most common situation for this to occur is at houses that are on a stepped foundation. If you have that situation, Shearwall Pro allows you to select different types of hold downs for the end of each shear wall. This overrides the strap or hold down selection above. If you want to reset all grid lines to be the same, reselect the pull down menu at the top of the table. At this point, you are finished with the lateral calculations for your building. Watch the next video for how to create shear wall drawings for your project. And here is looking ahead to what we're going to do in the next video. As you can see, we have all of the shear walls defined on every grid line, and we have all of the details put into the drawing, and we even created the structural drawing sheet that you submit to us to get the stamp on it. Make sure to like this video, then subscribe to our channel, and then ring that bell so you get all of the notifications for all of the next Shearwall Pro videos coming up. See you in the next video.